The derivative, one of your favorite calculus words. Recall that the slope of a line through the points A, F at A, and B, F at B is M equals F at B minus F at A over B minus A. Now from Algebra 1, you should remember y2 minus y1 over x2 minus x1. We are just giving our y values different names. If a line is tangent to a curve, then it intersects the curve at only one point. You know that from geometry. Here's your tangent line. Here's your secant line that intersects the circle or a curve at 2 points. So let's consider some point A, F at A, and some function, y equals f of x. The slope of the line through point P and tangent to our function is the limit as x goes to A of f of x minus f of a over x minus a. The tangent line is not this piece, which is the slope of the line, and it's the slope of the secant. The tangent line happens when we take the limit as x gets very close to a. So the equation of the tangent line can be found by using the point slope form of a line. You remember that from Algebra 1, y minus y1 equals m times x minus x1. Well, now with our new notation, y minus f at a equals m times x minus a, or solving this for y, we can move that f at a over. Now this is going to matter a lot in the near future and throughout the course. So you want to be sure to ponder this. We often discuss the slope of a curve in reference to the slope of its tangent line at its point of tangency. If we zoom in close enough on a curve, the curve almost looks like a straight line. We call this local linearity. If we consider a point P1 at AF at A and we get very close to A, say a distance of h units away, then that point is P2, which has coordinates A plus h and f of a plus h. In other words, we've moved h units away from A. And so the slope of our secant would be f at a plus h, the second y coordinate, minus f at a, the first y coordinate, over the second x coordinate minus the first x coordinate. That should look like your y2 minus y1 over x2 minus x1. But part of it simplifies. We can do the denominator a plus h minus a leaves us h. And this is your average rate of change. I call that AROC, average rate of change. If we take the limit of how close we allow P2 to get to P1, in other words, we're letting this value for h get very close to 0, then the secant line becomes a tangent line. And the slope of our tangent line has this formula, which is, the slope is the limit as h goes to 0 of f of x plus h minus f of x over h. This is your slope formula for a tangent line. You need to know that backwards, forwards, and upside down. I can also, instead of h, use this notation, delta x. That means the change in x. But the important thing is this gives us the instantaneous rate of change, IROC, instantaneous rate of change. Note that here we are in a situation where it says to see examples 1, 2, and 3 on pages 98 to 100. Be sure you do that. The derivative is a particular type of limit, also known as a rate of change. It takes on y values for specific values of x. It is a function, and as a result, it can be graphed. So the definition of the derivative of a function is, look at that notation, f prime of x equals the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x, or I could use f prime of x at the limit as h goes to 0 of f of x plus h minus f of x over h. Other notations that you will see for derivative include dy dx, y prime, the derivative with respect to x of function x, the derivative with respect to x of y. So our conclusion is the derivative of a function is the slope of the line that is tangent to the function at a particular point. So now it says to look at Forrester graphs of increasing and decreasing functions on 24AA. So go to that page. So these are nice little graphs, and what we're going to do is at points A and B, we're going to sketch a tangent line, and we're going to determine, is our function increasing or decreasing, and is it increasing rapidly or not as fast? Here is our tangent line right here at A, and you can see the slope is positive. The function is definitely increasing. The y values are getting bigger. Notice here our tangent line has a steeper slope than this one, and it appears that our graph is increasing more rapidly. If we look at number 2, see our tangent line here. Our slope is positive. The function is increasing. Here at B, our slope is negative. The function is decreasing. So if you look at these and just start to think about where the tangent lines are and what they're doing, you can determine if a function is increasing or decreasing. And that leads us to our next point. What does the derivative f prime of x tell us graphically? If the slope of the tangent line is positive, f of x is increasing, and here is how we write it in notation. F prime of x is positive. If we know that, f is increasing. If the slope of the tangent line is negative, f is decreasing. And it would look like this in our notation. F prime of x is less than 0. F prime of x is negative. F of x is decreasing. If the slope of the tangent line is 0, we are usually at a relative minimum or maximum value of the function. Not always, but a lot of times. So if f prime of x equals 0, f is at a minimum or a maximum value, usually, not always. The derivative gives us an indication of the behavior of our function. In class, we'll look at these two items, but important to know that the derivative is a rate of change. Where have you seen this in math and science? Well, rate is distance over time, or average velocity is distance traveled over time elapsed. So this is actually not really a new concept. Let's consider a function where distance is a function of time. Time is in hours, and distance is the distance in miles traveled on a trip in a car. So if f at 0 is 0, meaning at time equals 0, we haven't gone anywhere. After 1 hour, we've gone 40 miles. After 2 hours, we've gone 90 miles. Well, you know that we've gone farther in the second hour, so we sped up clearly. We can find the average velocity during the second hour of the trip by looking at the distance traveled over the time that's elapsed. So f of 2 minus f of 1 over 2 minus 1, which is 90 minus 40 over 2 minus 1, or 50. 50 miles per hour is what our rate was in that second hour. Below is the graph of the function with average velocity line drawn connecting the time is 1 and 40 miles traveled, and time is 2 and 90 miles traveled. You can see this just is a graph of possibly what happened on this car trip. Look at that. It looks like we slowed down a little bit, but then we sped up. Maybe we had 2 hours to get this 90 miles. The average velocity over any interval is the slope of the line called the secant line, which joins the endpoints of the interval. This is also called the difference quotient. It gives the average rate of change of y with respect to x, or delta y over delta x. Graphically, the difference quotient is the slope of the secant line connecting these 2 points, f at a with a plus h, f at a plus h. So if we look at this little diagram here, and here's our point A and here's our point B, and this is part of that last graph where we did this, okay? Here is A, where I am, and a plus h is after a certain amount of time has elapsed. Here's my y value, f at a, and my y value here is f at a plus h, okay? But our average rate of change would be this y value, f at a plus h, minus f at a over a plus h minus a. That's our average rate of change. What would make instantaneous would be taking the limit as h goes to 0. You might want to pause the video to write all this down. Okay, our next example. Mary is a swimmer who trains in a 50-meter pool. Let f be a function that pairs her distance from one end of the pool with time t. Below are some values for a recent swim. So she's in a 50-meter pool. So when she goes there and back, she's actually traveled 100 meters. Look at her times. Notice this is 3 seconds. This is 5.4, 6.2, 6.2. What's happening here? How come this one was so fast? Well, remember, probably pushing off from the wall or diving in. Okay, and she comes down here to 50. And again, look at from 50, she's turned around. And so what's she done? Taken her less time to travel this distance. That's why, because she probably pushed off from the wall and so forth. Okay. Find Mary's average velocity over the whole swim. Well, if we just start with our distance and our distance, we would have 0 minus 0 over 60 minus 0. This 0 minus that, but that's not what happened. She actually traveled 100 meters. So you had to pay attention to what was going on in the problem. Very typical in calculus. So 100 minus 0 over 60 minus 0 is 5/3. Notice my units, meters per second. We want to pay attention to that. Okay, 1.6 meters per second. So now we're going to estimate Mary's velocity at t equals 14.6. Now something very nice is happening at 14.6. 14.6 is exactly 6.2 seconds away from here and exactly 6.2 seconds away from here. This is an unusual situation, but it might provide some interesting results. So we're going to take a symmetric difference quotient. Symmetric means we're going to go the same distance from either side of 14.6. So I'm going to go 6.2 seconds this way and 6.2 seconds that way. And I have these y values that are paired with those two differences in time. So symmetrically, 40 minus 20 over 20.8 minus 8.4, which gives us 1.61290 meters per second. Now, I can also do a difference quotient of a forward difference quotient, which means using this and moving forward. And I can also do a backwards difference quotient, which uses this and moves backwards. So my forward difference quotient would be 40 minus 30 over 20.8 minus 14.6. And my backward difference quotient would be 30 minus 20 over 14.6 minus 8. You need to recognize what these are. Sometimes one is more convenient than the other. All of these are about the same. It's not always the case. In the time interval h between our endpoints of the interval a and a plus h, if that time interval is made small enough, this secant line will become a tangent line at the endpoint a corresponding to the x-coordinate a. This is called the instantaneous velocity and is symbolically represented like this. Instantaneous velocity, instantaneous rate of change at time equals a is the limit as h goes to 0 of f at a plus h minus f at a over h. Very important formula. You might want to pause the video and write down what you see before I explain this problem. Using the limiting process, the definition of the derivative, that's what the limiting process is, to find f prime of x. So if I'm going to use the definition of derivative, that would be like delta x goes to 0, or I could also use h goes to 0, okay, either one, to find f prime of x if f of x is 1 minus x squared. So there's our function. So to find our derivative, it is a limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. Now, f of x plus delta x means here in our function f, everywhere I have an x, I'm going to put x plus delta x. So this becomes 1 minus x plus delta x, the quantity squared. Now, that's just this part of the definition, minus our function. Notice parentheses matter all over delta x. This looks terrible. Now we're going to do some algebra. What algebra would that be? We can distribute the negative. We also are going to square this binomial, but remember it is inside a parentheses following a negative sign. I like to call this aloha, a lot of horrible algebra. Aloha, a lot of horrible algebra. So first of all, I'm going to write 1 minus. I'm going to leave the parentheses. I'm going to expand this. You should be able to expand a binomial. A plus b quantity squared is a squared plus 2ab plus b squared. So x squared plus 2 times x times parentheses delta x plus the quantity delta x quantity squared. That is just expanding this binomial, minus, let's go ahead and distribute that negative. And now we need to go ahead and distribute that negative. So distributing this negative across that expanded binomial, and we have this. Now we're going to combine similar terms. You'll notice terms drop out. What do you now see? You see that we have delta x common to two terms. Let's factor it out. That leaves a negative 2x minus one more delta x. But now look at what we have. We now have something where I can substitute delta x equals 0, because as delta x moves to 0, this goes to 0, and I am left with negative 2x. And that is our derivative function. Seems like a lot of work. It's just algebra. It's not real hard. Takes time. But here's the beauty. Now I can answer the question, what is the slope at 3, negative 8? I have a derivative function. When x is 3, the slope would be, substitute 3 in there, negative 6. So that would be the slope of the tangent line at 3, negative 8. What is the equation of the line tangent to the function at 3, negative 8? Well, we know our point slope formula of a line. So my point is y minus negative 8, so y plus 8 equals slope times x minus 3. That's your point slope form. I can move the 8 over, write it like this. I could also distribute the negative, write it in slope-intercept form. You don't have to do that. You can leave it just like this, unless I ask for it in slope-intercept form. Now, there is an alternate form of the derivative. That was a lot of work. What was good about this is it lets us find a derivative function. So if I wanted to know the slope at 10, the slope when x is negative 5, I can do that. There is another form. This is the form when you want to find a slope of a tangent line at a specific point. Notice f prime at c, the limit as x goes to c of the function minus the function evaluated at c over x minus c. Let's look at that same problem a different way. Using the alternate form. Here's our function. Okay. I want the slope of the tangent when x is 3. So that means c is 3, so I need f of c, which is f at 3, which we know to be negative 8 from the previous page. Here's my formula. F prime at c is the limit as x goes to c of f of x minus f of c over c. So f prime at 3 is the limit as x goes to 3 of here's f at x minus here's f at 3, parentheses matter, over x minus 3. Once again, we have aloha. And look what we get here. 9 minus x squared over x minus 3. Now that's pretty tricky there. 9 minus x squared is the opposite of x squared minus 9. So you could take the negative out and make this x squared minus 9 and then factor that. Or you could recognize that if we want to switch the order of x minus 3, I can factor out a negative and lets me do that. The reason I want to do that is this factors to 3 plus x, 3 minus x. I want to cancel the 3 minus x's. And notice that this negative sign down here comes back up here. And now I can substitute. I wanted to know when x was 3, and there we go. The slope at 3 is negative 6. Now, what if I wanted the slope at 5? If I use the alternate form, I have to go through this whole process again. So you can see that the definition of the derivative, which is this method, actually gives you something very useful for lots of situations. So a function is differentiable. That means a derivative can be found at some c if it has to be continuous. Okay, so we learned that. If it is smooth, there is no cusp or corner point or sharp point, and it does not have a vertical tangent. Why is that? Because the slope of a vertical line is undefined, which would mean we'd have an undefined slope. Remember that this is your definition of continuity. And we will look at a handout on left and right-hand derivatives in class. Again, this is just reiterating things we've already done. Read through it. You might want to write the information down there that's at the bottom of the page. Your TPs for section 2.1 are 5, 13, and 25. See you in class.